We're covering our third lesson over circles today, and today we're going to be talking about tangent lines. Now, don't think SOHCAHTOA, like sine, cosine, tangent. Don't think that tangent in right triangles. When you see this, this is totally different, and we're talking about circles, so tangent means something totally different here. Now, let's jump right into it. A tangent line is what we're talking about specifically today. So a tangent line is a line that intersects a circle at exactly one point. So let's draw one. So if I have a line that touches the circle just in exactly one place, so really it like just grazes the circle. So let's say that my circle touched just right there. So like just grazes the circle. I'm going to call this tangent line, I'll name it with 2 points. Maybe we call it like line AB. That would be a tangent line, touches the circle in one place. There is something I want you to label here. So point B is where my line touched the circle. So that point has a name, and it's called the point of tangency. Okay, so where your tangent line does touch the circle, that's called a point of tangency. Now, there's 2 theorems that go along with tangent lines. So 2 things that we can prove, we're just going to point them out. So the first theorem says a radius drawn to the point of tangency is perpendicular to the tangent line. And honestly, you guys, the second theorem is kind of like an afterthought to all of this a little bit. So really, this first theorem, this is what you need to know to be able to complete these types of problems. So I put a star there. Now, let's draw in what they're talking about here in this theorem. So they say a radius, so I know how to draw a radius. If I draw a radius to the point of tangency, which is point B on my picture, so if I start from the center and I draw a radius right there to the point of tangency, I know that that radius is perpendicular to the tangent line. So really what they're trying to tell me is that it makes a right angle with the tangent line. That radius does. So when I see perpendicular, I think 90 degrees, so that would happen right here. Okay, so if you see tangent, know that you can draw a radius to the point of tangency, and the tangent line and the radius make a right angle. Okay, so that is the biggest thing that you need to know to complete these problems. So let's check out what some of these will look like. So I've got 3 examples here. Example 1 says, given that ML and MN are tangent, so if you see tangent, you should think to yourself, okay, I know there's probably right angles going on. They say tangent, they're trying to point out 90 to you. I know that those 2 are tangent to the circle, so I want to find the value of x. So first I'm going to go in and mark my right angles. So here's ML right here. It looks like L is the point of tangency, where it touches the circle. So if you draw a radius to that point, where those 2 meet, that creates a right angle. So right there is 90. MN, over here, this is also tangent. So where I draw a radius to point N, which is the point of tangency, that's going to create a right angle right there. Okay, so if I really just think about kind of the shape now, and that's what they'll do on these problems. Like, yes, these are circle problems, but we're going to be looking at right angles with tangents. So you'll see a lot of right triangle stuff. This one's a quadrilateral, so it looks like a kite. So I should know that there's 360 degrees in this quadrilateral, in this kite. So I have 3 of the angles. I just need to find x, which is the 4th. So all I'm going to do is take 360, bad glare, and I'm going to subtract off the 3 angles that I have. So let's subtract 117 and the 290s. And whatever's left inside your quadrilateral, that would be x. so 63 degrees. Example 2 says, oh, this is weird, find the area of the circle. Okay, so I know eventually I need to do pi r squared, what we were doing in the last lesson. To do that, I need to find the radius, which is this OB piece here. They called that x. I need to find that. Now, something that example 2 and example 3 don't say that they will on like an exam is they'll say like lines that appear to be tangent are tangent. So if it looks like one of these sides of your triangle only touches the circle once, it's okay to assume that. They should have noted that here. But AB is a tangent line. It only touches the circle at point B. So where they drew that radius in, you've got a 90-degree angle being created right there. So I know that I can mark that, and that's going to help me find x because now I'm looking at a right triangle. Okay, so I know that if I have a right triangle and I'm trying to find one missing side when I have the other two, I can just do Pythagorean theorem. So I can do x squared plus 15 squared equals 17 squared. We all know how to do Pythagorean theorem, so let's kind of fill that in here real quick. So I'd subtract over 225 and get 64. So then square root, okay, x would be 8. So that's the radius. The radius is 8 there. Now I can go and find the area because I know the radius is 8. So pi times 8 squared, 8 squared 64, so the area would just be 64 pi. Okay, number 3, same thing. There should be another note here, and you'll see that like on practice problems and on exams, but it'll say lines that appear to be tangent are. So this line right here, or this side of the triangle, looks like it's just touching the circle right there. So that's a tangent line, that's a point of tangency. So where they drew the radius in, right there, that's 90. Okay, and same thing, now I see a right triangle. So I'm going to think Pythagorean theorem to find this x value, which is what they want me to do. Ooh, this is weird because of this side right here. I know that this is x and this is x. Those are both radius pieces, so that makes sense that they're both labeled x. But the 7 is just from here to here. So that's weird. This whole side length is not just 7, that's just that piece. So you're going to have to write something to represent how long this side is, the hypotenuse. You need to add these two pieces together, and you need to say that that hypotenuse length is 7 plus x, which people mess that up. That's the most commonly missed thing on this type of problem. Okay, now I can set up Pythagorean theorem. So I would do x squared plus 10 squared equals, the hypotenuse is 7 plus x squared. Okay, obviously I know that's x squared plus 100. Be careful when you go to square this 7 plus x because you have to FOIL that, which it's been a long time since you've done that maybe, but you have to multiply 7 plus x times itself. So you're really just distributing the 7 here. So 49 plus 7x, and then distribute the x. I get something like that. I'd combine the x's. That'd be 49 plus 14x plus x squared. Okay, so that's an Algebra 1 skill. Hopefully that's not totally foreign to you, but that would be what I get here when I square that 7 plus x. So now I can keep going. I need to combine like terms. So notice the x squareds. I would like subtract this one from the left to bring it over here to the right. And this is perfect because they both cancel out. So it's not a quadratic. You won't have to do like quadratic formula or anything, which is nice. Okay, perfect. From there, we all know what to do. It's just a two-step equation. So I would subtract the 49. And then I would divide by 14. So not the best number. They didn't tell me how to round it, so I always say if they don't tell you, you can kind of do what you want. So I'm just going to say x is about 3.6. Cool. All right, on the back, so I told you there were 2 theorems that we're going to talk about today. The first one, this is the big one. Tangent line, a radius, they are perpendicular, make a right angle. The second theorem is the one that's kind of like just a small afterthought, but it's still referring to things about tangent lines. So here's what it says, and we've got a little visual here. It says that 2 segments that are tangent to a circle from a point that's outside the circle are always congruent. Again, it's a theorem, so this is something we can prove. Here's what it's showing you though, and if I use this diagram here, they're saying if I've got 2 different segments that are tangent to the circle, they only touch the circle one place, and they come from a point that's outside the circle. So here's kind of what they're talking about. Point E is this point outside the circle they're referring to. Okay, you've got 2 segments, so let's see, one here. CE, that's tangent to the circle. It only touches the circle at point C. And then ED, this is a tangent line. It only touches the circle at point D. So I've got 2 tangent lines that come from this point E outside the circle. If I just think about the segments from like the point outside the circle to the point of tangency on both ones, those 2 segments are always the same. So that piece and that piece would be congruent. Or I could write like, all right, CE is congruent to DE. Those 2 segments are always the same. So here's how you kind of like put that into play. They've given you a picture and they say find the perimeter of ABC. So find the perimeter of the triangle, given that this circle O is inscribed in the triangle. And remember, inscribed, we did a lot with this word first semester. Really, I just think of that as like inside, so the circle's inside the triangle. Realize that inscribed also means that the circle is tangent to the triangle in 3 different places, once on each side of the triangle. It's like the circle fits perfectly inside the triangle. It's tangent to side AB, so D is a point of tangency, F is a point of tangency, E is a point of tangency. Okay, so when this happens, we can use this theorem number 2 to work out the perimeter. So if you kind of just like look at parts of this picture, like say if I ignored all of this and just kind of looked at this part, it looks really similar to what we had up here. So like DB and EB, those 2 segments start from point B, this point outside the circle, and they're both tangent to the circle. So therefore, this theorem holds true. Those 2 pieces at that little corner are always the same. So if DB is 15, EB is 15. The same thing happens over here, you guys. AD and AF are both tangent to the circle, and they both come from point A. So those are congruent. If AD is 10, AF is 10. The same thing happens down here. 2 segments, both stemming from point C, so if this one's 8, that one's 8. Okay, so now I can work out the perimeter of this thing. I'm just going to add up all the little segments. So I'm going to start with 10. So I would do 10 plus 15. If I did this side, plus 15 plus 8. And then those 2 pieces, 10 and 8. That would be my full perimeter, which is 66. Common mistake, people will just leave off one little piece. So maybe like mark where you start or like cross them off after you add them up. Don't leave anything out.